The number of homomorphism of Z onto Z is. We need to find number of onto homomorphism. That is, if F is a homomorphism from Z to Z, then we have to find number of onto homomorphism. Onto homomorphism, it is clearly understood by the word onto. We are interested to find homomorphism from this to this point. We know that Z is generated by two elements 1 and minus 1. Homomorphism, normally we understand that homomorphism preserve algebraic structure, means either plus multiplication, or if any other algebraic structure, then homomorphism preserve. It means that elements of the domain, if follow some rule, then its image also follow some rules. So onto homomorphism, number of onto homomorphism will exist if they generate these two elements generate image. It means only two onto homomorphism exist because of image set codomain has two generators 1 and minus 1. It means that they have pre-images in this and generated by generate entire domain. So there is only two homomorphism. So option C is correct. The remainder, when 7 raised to the power 1000 is divided by 24. You can solve this problem by Euler theorem, or Fermat theorem is the extension of Euler theorem. So you can apply Fermat theorem also. Fermat theorem says a raised to the power p is congruent to a mod n. Condition is that GCD of p and n must be 1, and one more condition, p should not divide a. If these two conditions are fulfilling, then you can apply Fermat theorem easily. So consider value of a is 7 and value of p is 5 and n is 24, it is given. So 7 raised to the power 5 is congruent to 7 mod 24, and we know that 7 square is 49 and 24 2 is 48, so 1 will be remainder. It means that 7 raised to the power 5 whole square is congruent to 7 square mod 24, and we know that this one is equivalent to 1 mod 24. Now you got 1, so you can apply any power, you always get 1. So 5 2 is 10 and we need 7 raised to the power 1000. So make 100 here. So let G dot be a group and H be a subset of G, then H is a subgroup of G. If AB are two elements of H, implies AB belongs H. For all A belongs H, A inverse also belongs to H. AB belongs to H implies AB inverse belongs to H, and in option D, AB involve AB in H, then B inverse A inverse in H. After seeing options, you can directly tick the answer C. But other options, why fail? You should know these one. Because if we are picking any two elements, then all four properties will be satisfied for a group: closure, associative, identity, and inverse. If a star or any other operation is given, it is binary operation. There is no need to check closure property, because saying that binary operation, we say a binary operation whenever it satisfies closure property, otherwise not. If it is simple an operation, then we need to check closure property, otherwise there is no need to check. But here dot is a operation, and normally because J dot is a group, so it is binary operation and it will satisfy for properties. Now H is a subset of G, and we check or say H will be a subgroup of G when H has same operation induced on H, induced on G. So for option A, if we are picking two elements from H, implies that AB belongs H. It is only closure property satisfied here, but not inverse and identity element we cannot satisfy using this condition. So option A is not necessary part. For option B, if for all, if A in H, then A inverse belongs H. Means for each element have inverse in H. So we can say H is a subgroup? No, because of we can't prove closure property. Closure property because of elements are coming from G. It doesn't mean they will satisfy closure property. Yes, they will satisfy closure property, but it may be identity they cannot prove using only this condition. Option C is correct, and we know that option C is one step test for subgroup. Now where is option D is fail? If AB are in H, then B inverse A inverse also H. It means that this property is saying elements have closure property, elements satisfying closure property, but particularly we say closure property for all elements, but they are combining only inverse element. Suppose A inverse B, and this is element another element C. Suppose this is H. If we are picking an element A and B, then B inverse A inverse in H. But if we are taking A and C, then according to this condition, C inverse A inverse in H, but C inverse is not present in this set. So closure property partially satisfied here, but not for all elements. So only correct option is C. Let to permutation Z and mu is defined as given, then both Z and mu are even, both Z and mu are odd, even and odd about Z and mu. How to tell about a permutation is even permutation or odd permutation, or precisely how to explain parity of permutation. A permutation said be even if number of transposition is even. A permutation said to be odd if number of transposition is odd number. As Z is given to us, then 1 is going to 2, 2 is going to 4, 4 is going to 3, and 3 is going to 1. So first cycle is this, and then 1, 2, 3, 4 used, 5 is going to 6, and 6 is going to 5. So Z can be written as a disjoint cycle like this. So write this permutation Z in transposition form. So 1 is going to 3, 1 with 4, 1 with 2, and this is 5, 6 as previous one. So 1, 2, 3, 4. There are 4 transposition. So Z is even permutation. So Z is odd in D option. This D option is wrong, and B is also. Now true options is either A or C. So again, find number of transposition of mu. 1 is going to 5, 5 is going to 1. So first cycle is 1 5, 2 is going to 2, so this is single length, so there is no need to write. 3 is going to 4 and 4 is going to 3, so this one 1 2 3 4 5 and 6 is going to 6. So number of transposition is 2, so mu is also even permutation. So Z and mu both are even permutation, so option A is correct. Which of the following statements is true? In option A, in every cyclic group, each element is a generator. This statement is false. You can consider a cyclic group Z. This is cyclic group generated by 1 and minus 1. So not all elements are its generator because of given is in every cyclic group each element is a generator, so this statement is false. In option B, 1 and 3 are generators of the cyclic group Z4. Generators generator of Zn are which are coprime with n and less than n. So 1 GCD of 1 4 is 1 and GCD of 4 3 is again 1. So 1 and 3 are generator and total number of generator in Zn is equal to phi n. Euler-Totin function, you can find number of generator in Zn. So statement B is true. Every set of numbers that is a group under addition. So you can consider R plus is a group under addition. Is also a group under multiplication. Every set of number that is group under multiplication is also a group under multiplication. Not. R dot is not a group because of inverse of 0 doesn't exist. Every subset of every group is a subgroup under the induced operation. Again you can consider R plus. This is a group, but n plus is not a group because of inverse elements of natural numbers doesn't exist in set of natural number. So again this statement is false. So correct option is B. The number of elements in the cyclic group Z42 generated by 30. This question can be solved easily with this formula. Order of a raised to the power r is equal to n upon GCD of n with r. Generated by 30, we know a theorem. Subgroup of cyclic group is cyclic. Also generated by 30, saying that subgroup is cyclic. So generated by 30, it means then 1 star 30, 2 star 30 star is the operation on Z42. Normally operation induced on this is addition modulo 42. So this star normally addition modulo 42, 3 into 30 and so on. So you can find elements of the subgroup. So it may be 6, 12, 18, 24, 30 and so on. Normally how many elements, because of this is cyclic, so cyclic group of finite order, so elements in this set will be finite. By the Lagrange theorem we know that order of the subgroup divide the order of the group. Group has 42 order, so factors of 42 are 2, 3, so write comma 2, comma 3, comma 6, comma 7, comma 14 and comma 21. So possible order of subgroup may be this or one of them. And we know that consequence of Lagrange theorem is that order of subgroup, if it is cyclic and generated by A, element A, then order of this is same as order of element. So order of subgroup is generated by 30. So in place of R, put 30. So n is 42. GCD of 42 comma 30, and GCD of 42 comma 30 is 6. So 42 divided by 6, answer is 7. So which one option is giving 7? Option C is our right choice. So keep remember how to find this order, or in this type of problems always keep remember this formula, apply this formula directly and find the answer. The number of abelian group of order 24 up to isomorphism is. This problem asked in two different way. One way is written already, and second way is find the number of non-abelian group, or says up to isomorphism of order 24. These are the two ways to asking questions. So number of abelian group of a specific order, number of abelian group up to isomorphism or non-abelian group of a specific order of order something can be easily find, as order of G is given 24, and we can write 24 as a 2 raised to the power 3 and 3. 8 3 is 24. This is perfect. These powers, either 3 or 1, normally known as Ni. Ni means prime powers. So number of non-abelian group of order 24 will be product of partition of Ni when I is running from 1 to R. Here R is 2. So partition of 3 is 3. How? 3 can be written as 3, another 2 plus 1 or 1 plus 2, and last one is 1 plus 1 plus 1. So there are 3 way to write partition. And partition of 1 is 1. So 3 into 1 is 3. So option C is correct. The characteristic polynomial of this matrix is. Here are possibilities of given characteristic values. So in option A, so first check that what is the trace of this matrix. 1 minus 1 plus 2 plus 0. So trace is 2. Means characteristic polynomial give the idea of trace. So find which one characteristic polynomial is giving the exact idea or somehow related idea of trace. So in option A, x square x minus 1 whole square. If this is characteristic polynomial, what are the root of this polynomial? X is equal to 0, and this is 2 times, and x minus 1 whole square is 0, means x equal to 1 and 1. So these are 4 roots, 0 plus 0 plus 1 plus 1 giving 2. So this is the possibility of characteristic polynomial. Now check option B. In option B, x square x plus 1 square equal to 0. Now check what are the roots. So x equal to minus 1, 0 and 0. These are the possibilities of roots or eigenvalues. So their sum is minus 2. So this is not the possibility. So option B discard. Now check option C. Option C is x square minus 1 is 0. This implies that x equal to 0, 0 2 times, and x square equal to 1. So value of x is plus minus 1. Both value we will consider. In positive case we are done, but in negative case we are not okay. So option D discard, because of we have the possible eigenvalues minus 1 also. And in option D you can see x square plus 1 means 2 eigenvalues are 0, and other two are minus x square equal to minus 1. So complex eigenvalues. and sum of complex eigenvalue exists here. So this is not possible. So correct option, which was option A as a possibility, now confirm this is correct option. Let W1, W2 be two subspaces of vector space V such that dimension of W1 is 4, dimension of W2 is 5, and dimension of W1 plus W2 lies between 5 and 8. Then dimension of intersection can be. Here options have two dimension, means possibility of intersection dimension, for example 1 or 2, 2 or 3, 3 or 4, 4 or 5. Which one option is correct, we need to tell you. Now dimension of W1 is 4, dimension of W2 is 5, and dimension of W1 plus W2 lies between 8 and 5. Then asked about dimension of intersection, we know a rule: dimension of intersection is equal to dimension of W1 plus dimension of W2 minus dimension of W1 plus W2. This is rule, or you can say formula. As dimension of W1 is 4, dimension of W2 is 5, minus dimension of W1 plus W2. Now possibility of dimension of W1 plus W2 is either 6 and 7. There are two possibilities of this dimension. So for example, once you put 6, then 9 minus 6. 9 minus 6 give you 3, and 9 minus 7. When you put dimension of W1 plus W2 is 7, means 9 minus 7 give you 2. So dimension of intersection is either 2 or 3. According to this calculation, we can say option B is correct. Dimension of intersection. Dimension of intersection we normally know because of dimension of W1 is 4 and dimension of W5 is 5. So normally we can check that dimension is always, dimension of intersection is always lies between or min values less than equal to min value of 4 and 5. So min value is not good here. Uh, you can understand this one because of dimension of intersection will be less than, not exact, less than equal to 4 and 5. Using this fact we can eliminate option D directly because of dimension is 5 possible. Possibility of dimension of intersection is 5 here, so option D discard here, and correct option is B. Let the sequence xn is defined by x1 is 1 by 3, x2n is half, x2n minus 1, and x2n plus 1 is 1 upon 3 plus x2n for all natural number. This is the structure of xn, how this is defined for all natural number. This is for even terms and this is for odd terms. Now options are: limit superior of xn is half, limit inferior of xn is 1 by 3. Similarly, limit superior and inferior is asked in all four options. So first we compute what is limit superior and what is limit inferior for this particular sequence. Limit superior is infimum of all limit points, and limit inferior is supremum of all limit points. Because this sequences first term is 1 by 3, second term is 1 by 2 x1, and x1 is 1 upon 3. So 1 upon 2 into 1 upon 3, this is equal to 1 upon 6. x3 is 1 upon 3 plus previous one. So 1 upon 6, this one equal to 3 2 is 6 plus 1 divided by 6. This means half. So few terms of the sequences are 1 upon 3. This is first term. Second term is 1 upon 6. And third term is 1 upon 2. You can compute other terms as x4. x4 will be 1 upon 2 into 1 upon 2. This is equal to 1 upon 4. And x5 is 1 upon 3 plus 1 upon 4. This one equal to 12 as a LCM. So 4 plus 3 is 7 by 12. So 1 upon 4, 7 by 12. So you can identify this sequence is not monotonically increasing or decreasing, but this sequence is bounded. All terms are positive, so you can say 0 is lower bound, and defined terms are by half, and this is coming from previous one. So all terms are near about 2. So all xn either less than equal to 2 or greater than equal to 0. So we have two lower bound 0 and 2. When sequence is bounded, now sequence is bounded, so limit superior is largest limit point, and limit inferior or lim inf is smallest limit point. So for these few terms, we can say that largest point is half. So limit superior may be half. Remember the used term may, not confirm. So look for options. Limit superior is half in option A. Similarly in option B. In option C, 1 upon 3. And in option D, 1 upon 2. So option C discard here. Now we have three possibility, option A, B and D. Means if anyhow we get the idea about limit inferior, then we are done. So limit inferior, few possibilities are 1 upon 3, 1 upon 3 square and 1 upon 6. Now again come to these few terms, you can say that 1 upon 6 is the smallest, in these few terms. I am not saying in all terms 1 upon 6. This is by trial and error. 1 upon 6 is smallest in these few terms. So possibility of limit inferior is 1 upon 6, and limit superior is 1 upon 2. Is this in all these four options? Yes, this is in option D. So option D is confirm. Because here it is not asked about supremum or infimum. Supremum and infimum is slightly different from these, but for a convergent sequence they become same. Limit superior and limit inferior and supremum and infimum become same. So limit superior is half and limit inferior is 1 upon 6. Always keep remember, whenever sequence is bounded, then limit superior is largest limit point and limit inferior is the smallest limit point. To justify these two are limit points or not, 1 upon 2 and 1 upon 6 are limit points or not. So we have many subsequences which are converging to this one and this one of given sequence, not random sequence. It is, keep in mind, subsequences or sequences must from these given original sequences. The radius of convergence of this series, this is, to find radius of convergence we have normally usually two formulas. R equal to 1 upon limit of a n raised to the power 1 upon n. Sometimes this format is known as a root type format, and this one equal to limit a n upon a n plus 1. This is another form of finding limit radius of convergence of the power series. So whenever series is given to you a n x raised to the power n type means standard format, and you have a n equal to n raised to the power n means power contain n. So try this format because of powers cancel out. So r equal to 1 upon limit n raised to the power n 1 upon n power n into 1 upon n means one value. This one equal to 1 upon limit n when n is tending to 0. So we know normally limit of n is infinity. It means 1 upon infinity type means 0, or we can say approximate 0. So value of radius of convergence of this series is 0, means option A is correct. If an z raised to the power n is a power series with radius of convergence r, then the series converges absolutely for mod z less than equal to r. This condition is important. Converges absolutely for mod z less than r. Convergent absolutely for mod z equal to r. And last condition is this one. Means we have to tell about the convergence of this series and what is the members of z which are real number, sorry, not necessarily real number, but condition on those numbers which are either less than equal to radius of convergence or greater than equal to radius of convergence, or is in the neighborhood of radius of convergence. Somehow question is related to radius of convergence. Radius of convergence or interval of convergence is somehow different. Interval of convergence is gives precise way to say something where is series convergent, and radius of convergence is slightly less powerful than interval of convergence. So normally we find radius of convergence r by limit n tends to infinity un upon un plus 1, and another way is 1 upon limit a n raised to the power 1 upon n. Normally we use this concept, or directly we can find also somehow. This gives you radius of convergence. If summation a n x raised to the power n or z, sometimes as written here, normal structure or standard structure of power series is this one. In this case, suppose radius of convergence is r, then this power series will converge for mod x less than r. We are 100% sure about the convergence whenever absolute value of those number which are less than radius of convergence, power series will converge. But whenever equality hold, then this power series converges or may not be converged, means both case included here. So there is further investigation need to be checked. And for mod x greater than r, it is divergence or divergent series we say. So converges, it means In option A, equality hold. At equality, may or may not both possibility occurs. So we cannot include this option as a right choice. In option B, this is correct one. So I ticked here. And in option C, equality hold. It may be or may not be both conditions. Because of if this is radius of convergence at boundary point, R means at boundary points where series is convergent or not. Sometimes convergent, sometimes not. The series converges absolutely for mod z greater than R. This is normally or commonly known when mod z greater than R series diverges. So correct option is only B.